Hey, Braxton is with us. Braxton, how many classes do you have with me?
I have three: dynamic strengths and thermodynamics.
Oh my. Yeah, you're a glutton for punishment, Braxton.
Yeah.
Okay, well, welcome everybody. Let's see who else we've got here. We got a good crowd. We've got Nicholas, Taylor, Alex, Braxton, Bryce, and it looks like Julian, Nathan, Reagan, Mohammed. Got a really good class here. Now, I put something on content. What I did was I put those step-by-step way to solve thermal problems. Did anybody find that on content yet?
Yes, sir.
Good, good. And I also had all of the first and second laws there on content for you. I thought that'd be helpful. I'll tell you what I'm going to try to do. I tried this once before and failed. There's a button here called share screen. Now, if this doesn't work out, I might have to start all over. Just bear with me, guys. I'm always afraid whenever I do anything new. I don't know about it. It's just it's a human thing, but you guys do new things all the time. You're brave. Like taking this class, for instance. See, for me, teaching this class doesn't require any bravery because I've taught it since before you guys were born. But this scares me, guys. I'm scared, but I'm going to try it. I'm going to push this green button that says share screen. What I'm going to do is try to bring up that stuff I put on content for you, but you can get it on content. So why am I doing this? Because I want to see if I can do it. All right, here we go. Green, share screen. Push share screen. Okay, I did that. And it says go to file. What do you mean go to file? I don't know what they're talking about. Down here it says share. Do you suppose I should click share? I don't know. Click open Zoom meeting. You are screen sharing. I want to go to the file. I don't know how to get to this.
Do you have the file pulled up on your screen right now?
No.
Yeah,
We can see your screen.
Okay.
So just go ahead and open the file like you normally would, and we should be able to see it.
You're talking to a computer person, not a computer person.
what
All right.
are you?
Well, I'm going to try to pull it up. Now, how do I do that? Oh, gee.
Yep. We can see everything right now. So whatever you pull up, we can see so that you're good.
Okay. Now, how do I pull this up though? It's
You're
on
looking
this,
for that list of the steps to go
yeah.
through, right? So if you'll open a new tab and go to Blackboard.
Open a new open a new tab. You mean that little plus thing up here at the top?
That's the one, lowercase t.
New tab, it says. Okay.
And then you have that shortcut that says welcome right below that.
Welcome. I don't see any welcome.
Right under your toolbar or your search bar.
It says welcome
TCC.
TC.
Oh yeah,
TC,
welcome
app.
TCC. Yeah, welcome GCC. Do you think I should push it?
Yes, sir.
Yes.
All right, I'll push it. I pushed it. Yeah, okay, here we go. And now I want to log in, right? Log
Right.
into TCC. Okay, here we go. Excellent. You guys are helping me here. You guys got a great future ahead of you. You're not like me. You're not computer inhibited. All right, now Do I need to go to Blackboard and pull up my class?
That's what I would do.
Yeah, that's what I'm doing. Okay, I'm going to Blackboard. And I'm trying to pull up my class. And that circle thing is going around and around. And I need my course. Okay, I'm trying to find our course. All right, we're trying to find our course. This is our thermo class. And I did it. There's my thermo class. Come on now. Okay, now what we want is content. I'm going to push content. Boy, Jove, there it is. And I'm going to go down to where it says step to solve. Do I just click on that or what? Probably. Yeah, here we
That
go.
one.
Yeah, here we go. Boy, Jove. I think you've helped. There it is. Now, does that show up on your screen?
Yes, sir.
Wowee. Whoa, success. This is a big moment for me. Now, this first part's pretty cool. I've shown you this a couple of times before. Don't we always do that, make device sketches? Is everybody with me? Do you see it says make device sketches? Somebody say, uh-huh.
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 Yeah, there you go. Yeah. Yeah, that's the first step. And then the second step is decide on the model. You got to decide whether it's ideal gas or not. Now, how do I scroll down just a minute here? Yeah, there we go. And then the third step is a PV diagram. There you go. Or TS. We're learning how to do TS now. Somewhere, step 4, you got to decide whether it's control mass or control volume. Now, what are we going to do today? I'm going to do a problem here. Well, it's really a control volume, but it's a special kind. It's called a transient process. Number 5, first and second laws. Well, see, I've listed all those for you here. You've seen them before. We'll talk about that in just a minute. Then you do the math, and you do it either in SI or in British engineering. Yeah, then you check the units, number 7, check the answers. Now let's look at these first and second laws. That's good stuff. Okay, there they are. There's the first law for control mass, the first law for control volume. You should be familiar with those. Now you've had this before, this first law for transient processes. It's a little bit ugly, but we're going to use that here in a minute on a problem. Then the second law for control mass, there it is. There's the second law. And there's a second law for control volume. I think I've shown you that. I don't think I've shown you this last one, the second law for transient processes. But there it is. It's in your book. And now you have it. We have screen shared. And now I'm going to get out of screen sharing and get back into the world that we're more used to. I think what I do is click on this green. I want to get out of screen sharing. Oh, stop share. There it is. Stop. Hey, are we back to the world now?
Uh-huh.
Yeah, good deal. Well, that was a little bit nerve-wracking for me. But let's do that. Here, let me write down your where we are in this class. Your homework, and let's see. You've got some homework. This is November 10th. Your homework is, gosh, it's homework number 23, I think. Homework number 23. 792 and 7134E. They're due the 13th. I think they're available this morning. Those are available this morning. They're due the 13th. Well, what's the 13th? That's Friday. Today's Tuesday. There's that. And did you know you have an exam? Look here. November 12th. You know when that is? That's Thursday. Thursday, November 12th. Your exam 3 will be available. And do it for me and turn it in. It's on exam chapters 5, 6, and 7. And it's due the 15th. That's a Sunday. That's this Sunday at midnight. There you go. So there's your up-to-date stuff of what you're supposed to do. Do you have any questions on that? Okay. Well, that's all in your Blackboard. You can look it up. You didn't need me to write that. I want to do problem 776 now. It's a transient problem. And we're going to use that transient equation. Let me write it down. It goes like this. Well, I got room down here. I'll write it down here. It's a big old long thing. This is the second. Well, we need to write both of them, don't we? The first law and the second law. The second law goes like this. You'll find this on your content. I put it on your content. I think maybe I left out a summation sign, but it's not the end of the world if you leave out that summation sign. Now the first law, see, that's the second law for a transient process. Here, let me make some room and I'll write the first law. You all know you got this test and the homework there. You can read that in the Blackboard. First law, it goes like this. It's also a long, ugly thing. I'm leaving out a bunch of stuff. I'll put it in here. We don't need it for this problem we're going to do. Get a little bit lazy there. Yeah, they're kind of ugly there, but there you have it. And that's under content. So you can pull that up, or you can read your book. That's another thought. But I want to do problem 7, 76. And let me find it. 776. Okay, I found it. Okay, well, you know the drill. You draw a device sketch. So I'm gonna erase all this stuff. You've got all this. It's under content, and you can make a copy of it. All right, we're going to do problem 776. And you've got an empty can filled with R134A from a line. Here's your line. And there's a valve here. And there's this empty can. And the line has R134A. Saturated vapor. Now that should mean something to you guys. Saturated vapor on your PV diagram or your TS diagram. You should know where that is. At 10 degrees Celsius. And you're starting off, this thing is empty. Okay. And then later, see, this is going to be state one. Later, you open that valve and this refrigerant comes into your can that was empty. By the way, it's a 0.002 cubic meters. And the pressure at 2 is 200 kilopascals. They want to know the final mass in the can and the total entropy generation, and we'll do that for them. We'll do that. But first, let's find the values of. We know the incoming temperature is 10 degrees Celsius. Let's get the incoming pressure, the incoming specific volume. Why don't we get all this stuff? It won't do us any harm. We can look all this stuff up. Go to the back and help me find R134A. Here, I'll draw a PV diagram. Okay. Now we've got 10 degrees. Well, that's sort of in the middle. I'm looking at table B.5, R134A. 10 degrees is kind of in the middle. Let me draw it. Okay, I've drawn the 10 degrees. And the pressure there is 415.8. Does this show up on the, yeah, that shows up pretty good. Yeah, that's kilopascals. We need to do a TS diagram too. That would be fun. And you know what? We're located right there. There's state one, isn't it? No, that's not state one. That's the incoming state. But we just figured out the incoming pressure is 415.8 kilopascals. And we can get the incoming specific volume. It is 0.04945. Now I'm getting this from table B.5. If any of you are having trouble finding these values, just speak up and we'll slowly try to show you where it is. Okay, now let's get our incoming specific internal energy. I'm getting 383.67. Now you're supposed to put units on all this stuff. The incoming specific enthalpy. Let's see if I can find that. Well, it's 404.23 kilojoules per kilogram. And the incoming specific entropy is 1.7218 kilojoules per kilogram Kelvin. Ta-da! So we made a little progress now. We've got all the properties of the incoming refrigerant. But what about the state 2? See, state 1, it's empty. There's nothing in that can. We have the properties of the incoming refrigerant, but we don't have anything in that can to start with. But the pressure coming in was 415, but it's only, we're going to stop at 200. So see this valve here? Once the pressure reaches 200, we're going to shut it off. If you left that valve on, the pressure would go to 415.8, but we're not going to leave it on. We're going to stop the flow there. So you open that valve, and what happens is it's coming in there. Now we're going to shut it off. Now watch this out. There, I shut off the valve when it got to 200 kilopascals. So what do we know at that state 2? Well, we know the pressure. What else do we know? I don't know about the temperature. The way this thing works is when you fill these tanks, they get hotter. I don't know what the T2 is, but I think it's going to be hotter than 10 degrees Celsius. How are we going to find it? Well, I don't know. How about we try writing some of our equations? We have the first law for transients. I'm going to write it now. Here goes the first law for transients. It goes M2 U2 minus M1 U1. Well, there isn't any M1 U1. There's nothing in it to start with. So it's 0. Equals, now didn't they say it's adiabatic? Go back and read it. 776. Did they say it's adiabatic? Yeah, the filling is done quickly, so it's adiabatic. So here you have Q. I'm being lazy and not writing it out, but you've got this first law in content for you. I gave it to you in content. And then you go minus the work done. Well, there's no work done. All you did was open a valve and let in some refrigerant. There's no work done. This is the heat transfer, this is the work. And then this is the income flow rate times HI. And then there's a kinetic and a potential, a specific kinetic and a specific potential energy terms. We're not going to worry about them. Just forget them. We don't need them. Minus the exiting. There is no exiting. Mass comes in, but it doesn't go out. And so that's 0. That's it. Ta-da! We just wrote the first law. And you know what? The mass at state 2, whatever it is equal to the incoming mass. Let me write that. The mass at state 2 is equal to the incoming mass. Does that make sense? Whatever came in is what you have at the end. Okay. So you could do a little algebra trick here, and here's what you'll wind up with. You'll get U2 equals HI. Can you get to here with me? U2 is equal to HI. All right. Well, we know HI, look. We got HI here, I'll circle it. So that means we got U2. Huh, interesting. All right. Well, I need some room. We all know we got this empty can here, and we're doing 776. But I need some room to write stuff. And here's what we know. We know what U2 is. It's equal to HI, which is 404.23. Kilojoules per kilogram. And we know what P2 is. P2 is 200. P2 is 200 kilopascals. Okay, let's find it. You know what? I think we're in the superheated vapor region. So go to R134A, superheated vapor, 200 kilopascals. That's what I'm trying to find. There it is. There's 200 kilopascal. And what we want is a U2 of 404. Well, I don't see a 404. Oh, we're going to have to interpolate. But we can do that. Here, let me put it right here. At 200 kilopascals, I'm on table B.5.2. B.5.2. And they have a table there. They have V. They have T. They have V. They have U. We don't need the H, and they have S. Let me write this stuff down. The temperature there that I want is 30. And the V is 0.11889. Is this stuff showing up on the board here? Is it? Yeah, kind of, yeah. And the U is 403.10. I hope you can find these on table B.5.2. And the specific entry is 1.8549. 8549. We're going to have to interpolate. Now, the next temperature up is at 40 degrees Celsius. And at 40, the specific volume is 0.12335. Specific internal energy is 411.6 0.04. Specific entropy is 1.8836. Now you see what we want is 40423. To get that, we're going to have to interpolate. Here, let me put in a different color so that you can see it. See, what we want is 40423. 40423. Does that show up? Not very good. That red really doesn't show up too good. 40423. And what we need is the temperature. That'll give us the temperature at state 2. That'll help us plot it. We know what the pressure is. It's 200. Well, 200 is smaller than 415, so we know 200 kilopascals. We're going to go down. We're going to be down here someplace. And maybe further down than that. I don't know. We'll fake it here. But I'm going to pause and shut up for a tiny minute, and I'm going to let you find the temperature at state 2 by interpolation, the specific volume and the specific entropy. Go for it. You can do it. And then we'll check it here in just a minute. Well, I hope that you got some of those. I'll tell you what I got for T2. I got 31.4. Gee, that's hotter than 10 degrees. Remember, this came in at 10 degrees. We had 10 degrees coming in, but the temperature of that refrigerant went up to 31.4. Anybody get 31.4 degrees?
Uh-huh.
Yay, I'm so proud of you. Well, let me draw that. 31.4. Let me make this a little steeper down here like that. And see, 31.4 is kind of there you go. There's your 31.4. Now the pressure went down. See, the pressure went down to 200. Let me draw that a little steeper, maybe. Yeah, here we go. Yeah, there's your 31.4. Temperature went up. Pressure went down. You're coming in, here's your incoming. It's saturated vapor. And you're going to state 2. There you go. The pressure is smaller, but the temperature is hotter. That's what happens when you fill these tanks. They get hotter. And I also got the V. The V is, let's see, it's 0.11952. And I got the S. The S is 1.8590. So we know a lot of stuff about state 2. Here, we could list it if you wanted. The temperature at state 2 is 31.4 degrees. Got hotter. The pressure at state 2 is 200 kilopascals. The specific volume at state 2 is 0.1. Did anybody get 0.11952 like I did?
Yes, sir.
Yay, good going. And the specific internal energy at state 2 is, well, we started with that. Remember, we found that because it was the same as the specific enthalpy that it was incoming. See the 404.23, the 404.23? They're the same. And then the specific entropy at state 2, I got 1.8590 kilojoules per kilogram Kelvin. So we know a lot of information about state 2. You know, the temperature and pressure and a lot of things. I think it's time to go to our second law of thermodynamics. Now, it would be nice to know what the mass is at state 2. How could we do that? Here, there's some room right here. Here's how you can figure this. The mass at state 2 would be the volume at state 2 divided by the specific volume at state 2. Well, what's the volume at state 2? Well, that's the same volume that you had at state 1. It's 0.002 cubic meters. They give you that in the problem. And the specific volume, hey, there it is. It's 0.11952. 0.11952. Don't have room to write cubic meters per kilogram. But you can get the mass at state 2. Go ahead and get that, and we'll see how much mass we have. Well, it's not very much, but here's what I'm getting. The mass at state 2 is 0.01672. I ran out of room there, kilograms. So we know the mass at state 2. It's 0.01672 kilograms. What is that, 16.7 grams? Not very much. About the weight of 3 nickels. Not very much. But that's what our mass is. Now what were we supposed to find? I got lost. Let me read this problem again here. Well, we're doing problem 776. And we've come a long way. We found out a lot of stuff. Find the final mass in the can. Well, we did that. That's the final mass in the can. It's 0.01672 kilograms. All right. What else are we supposed to do? The total entropy generation. All right, to do that, we need our second law for transient processes. We're going to have to sacrifice this first law down here, and we're going to have to write the second law. Here goes. We're going to write the second law of thermodynamics for, see, it's interesting, but there's different versions of the second law, just like there's different versions of the first law. But the second law of thermodynamics, you have it there under content that I put on your course there. And what it goes M2 U2. Well, we know. Here, I'll write it for you. It goes M2 U2. Well, we know M2. We just figured it. M2. There it is. We got it. U2. Well, we know that too here. We got U2 minus M1 U1. Well, that's 0. It was empty. Remember? Equals heat transfer. Well, there is none. They said it was adiabatic. So that's 0. Plus the entropy generation term. That's what we're supposed to find. Plus your M dot incoming S, your specific entropy incoming, minus your exiting. Well, there isn't any exiting. Nothing exits. Everything comes. Wait a minute. This doesn't have a dot on it. I was wrong. It's like that. But look at here. We know what the incoming mass is. Well, it's the same as the M2. Did you know that? The incoming mass is equal to the final mass. So we know that, and we know the incoming specific entropy. Look, it's right here. Look, we know that. So we know that. Do we know U2? Boy, Joe, we do. We know U2, and we know M2. Hey, look at here. Here's an equation with only one unknown. We can do it. So this is called the generated entropy. The generated entropy is going to be M2U2, which is 0.01672 kilograms. I'll just go U2 minus the SI in this case. The U2 is 404. No, wait a minute, I'm doing something wrong. Yeah, here's where I went astray, guys. The second law has an S2 here, not a U2. I was writing the first law over again, but now I've got it right. It's M2S2 minus 0 because it was empty equals the heat transfer term, which is 0. It's adiabatic, plus the entropy generation, plus the incoming entropy term. All right. So let me do this right. M2 is 0.01672 kilograms. S2 is 1.8590 kilojoules per kilogram Kelvin equals generated entropy plus, well, the incoming mass is the same as that there, 0.01672, and the incoming specific entropy is the 1.7218. There you have it. Plug all that stuff in, and we'll have the generated entropy. And then we might have time to do another problem. Wouldn't that be fun? Okay, I got an answer now. Now here's the answer in the answer book. The answer book says the generated entropy is equal to 0.00226 kilojoules per Kelvin. And boy, Jove, 229. Well, when I did this, I get 0.002294.
That's what I
Let's
got
don't
too.
fight over it. Let's don't fight over it. Did you get a 0.02294? Anybody?
Yes, sir.
Yay, good going. Well, that's what the answer book says. It has a 6 there, but we are not going to change our majors because of that. We have solved a transient problem. Now, we haven't done the TS diagram. Dang. Do we have time? The problem is, do we have space? Do we have the room to put it in there? Here, I'll show you kind of how it goes. I need some room someplace. So, goodbye there. Let me make a hole here. The TS diagram, because I want to do another problem with you. You know where it starts off. It starts off as the incoming. And we have all of that information right here. I erased part of it, but there it is. And you know the pressure there. I usually do my pressures in blue. The pressure coming in was 415.8. Do you remember that? So it goes kind of like that. That's 415.8 kilopascal. And then what happens? Well, the pressure goes down, but the temperature goes up. So you go from I to state 2. Here's state 2. The temperature went up. The temperature went to 31. See over here, this temperature was what, 20? Or no, it was 10. And then the temperature goes up to 31 degrees Celsius. But the pressure went down. See, the way the pressure works is like this. And the pressure here is 200 kilopascals. That's how your isobars look. Well, there's your process on the TS diagram, and that gives us time to work another problem. Yay, let's see what we can do here. Any questions, though, before we move on? We did problem 776. It's a transient process. We used our first and second laws, which I have put on content for you. Not that you really needed them. You've had them before, with the exception of that second law for transients. That might be new for you. I don't know. All right, well, we got a little time left. I don't know if we can get this whole problem done, but we can get a lot done. We've got half an hour. You can do a lot in a half an hour. And the one I want to do here is 7141E. E stands for Inglés, Senor. So let me find it. Let me find 7141E. Okay, 7141E. Initially empty 5 cubic foot tank. It's filled with air. It's good. See, we just did one with a vapor dome. This won't have a vapor dome. This is air. We've got a line coming in, kind of like we did before. Here's this line, and what we have is air coming in at 70 Fahrenheit and 15 psi. And it's coming in, and we have an empty tank. It's 5 cubic feet Okay, now there's state 1. It's empty. Now state 2, here's your tank now. State 2, you open that valve and it's filled with air until it is full. I get the feeling they're going to leave that valve open. You just open the valve and let it flow. And I think that at state 2, your pressure will be 15 psi. Does that make sense? It'll go to 15 psi and then it will stop because you only have 15 psi. It's not going to get any higher. Assume no heat transfer. Okay, Q is 0. There's no heat transfer. Find the final mass and the entropy generation. Okay. Well, it's kind of like what we did before. We don't have any vapor dome. It's not saturated vapor. We can't look up in the tables all the interesting things about it. So what do? Well, we can still write the first law. We have a first law for transient problems. And it goes, well, you know how it goes. I put it on screen share. It goes M2, U2. But I don't know what M2 is. And I don't know what U2 is. Minus M1, U1. Well, it doesn't have anything to start with. And that's going to equal the heat transfer term. Heat transfer. Well, there isn't any. They said it's 0. Minus the work. Well, there isn't any work either. There's no work. Plus the MIHI minus the MEHE. Well, there isn't any exiting. Well, by Jove, I think we're kind of back where we were. I think the M2 and the MI are the same in this case. Whatever goes in is what you got left at the end. And so you could do some algebra and you could say U2 is equal to HI. Does that make sense? U2, yeah, good going. Well, let's just look it up. If you know it's 70 Fahrenheit, and we might need Kelvin, just a minute now. 70 Fahrenheit is 459.67, I think. I hate to tell you anything wrong. Let me double check that. It is 459. So yeah, see, I haven't forgotten everything. And so what you have here in Rankine, you got to have Rankine. 67, 9. What do you think? 529.67 Rankine. There you have it. So we have our temperature. Well, so what? Well, we're going to look it up. We have some ideal gas integral tables here. And we're going to look this up on, it's got to be in English, senor. Help me find the English. ¿Dónde está? There it is. Yeah, here we go. Here's the properties for air. And what we need is 529.67. Well, they don't have a 529.67. I'll tell you what they have. At 520 Rankine, if you want the, now what are we trying to find? We know that the incoming temperature, this is the incoming temperature, this is TI, right? The incoming temperature is 529, and the incoming specific enthalpy is Well, you have to look this stuff up in the tables. 124, 383. Why don't we get the, yeah, that's enough for right now. We'll get that. And then this here is, well, let's just go to 540. And that is 129.180. But see what we want. We want 529.67. We need this. You know what that's going to be? That's going to be this HI. We can get that. We can get that HI by interpolating. You understand? So I'm going to shut up, and I want you to find what this HI is. On your mark, get set, go. Well, I wonder if you got what I got. When I did this, I got 126.70. Anybody get that?
Yes, sir.
Yay, there's two of us. Well, see, we just found this. We just found the incoming specific enthalpy, and that's equal to U2. So now we know U2. Here, let me write that someplace. How about up here? Yeah, we'll write it up here. U2 is equal to well, now wait a minute. No, that's T2. I'm getting mixed up here. T2, no, that's H2, isn't it?
Yeah, I think we found it. HI.
Yeah, we found the HI, and that's equal to U2. Okay, here, let me write that. Yeah, now I'm back on track, I think. I'm getting U2 is equal to HI, which we found to be 126.70, and I darn near fouled up there, but it's BTUs, isn't it? BTUs per pound mass, right? Because we're in English, senor. So I tell you what we have. We have U2, and you know what? We have P2. Look at here. We have P2 is 15, and U2 is 126.7 BTUs per pound mass. But I think we can get the T2 now. I think we can get it from this same table. I need some room here someplace. There's some room right here. It turns out that the specific internal energy is independent of the pressure. So we don't even need to worry about that 15 psi. We just need a 126.7. 126.7. Aha, look at here. I'm on table F.5. I'm on table F.5, and we're going to have to interpolate again. 720 Rankine has a value of U of 123, 167. And then at 760 Rankine, it's 130.118. But see, what we want 126.7 BTUs per pound mass. That's going to give us the temperature at state 2. See, you're coming in at 70 Fahrenheit, but I think this is going to be hotter. It'll be hotter than 70 Fahrenheit. And we're going to find out what it is right here. I'm going to shut up again. I want you to find this. You're going to have to interpolate. Go for it. See if you can do it. Well, I did that, and I got 740.3 something Rankine. Wonder if that's right.
Yeah, I got
I
that
did
too.
I wonder if we both did that right.
That's what I got.
I bet it's right. Did I write this down right for 720 Rankine? 123, 167, yeah. 131, 18, yeah. Yeah. 67. Yeah, I think I did that right. Okay, now we have our new temperature at state 2. We think the temperature at state 2 is 740.3 Rankine. When I did this before, I got 738 Rankine. I wonder maybe I made a mistake. I hate that. I think I wrote down something wrong. I bet that's right. Several of you guys got that. Now let's get that in Fahrenheit, shall we? Take the 740.3 Rankine and subtract the 459.67. We need Fahrenheit. Let me see what it is. There it goes. 740.3 minus 459.67. Gee whiz, I'm getting 280.6 degrees Fahrenheit. It got hotter, folks. Look here. It came in here at 70 Fahrenheit, but T2 is 280.6 degrees Fahrenheit. It got a lot hotter, didn't it? That's why they have to let these canisters cool off after they fill them, because they can be blistery hot. Okay, well, we got the T2 now. Now what are we supposed to do? I kind of got lost. Let me go back and read the problem again and see what we're supposed to do. We're doing 7141E. It's an English problem. It's with air. And we need the final mass. Well, how are we going to get that? Hey, I got an idea. I got an idea to find the final mass. I just need some room here. There's a little room right in here. How about P2V2 equals RT2? We can do that. It's air. Do we know T2? Well, boy, Juve, we do. Only you'd want to put it in Rankine. You'd want the 740 Rankine. But yeah, we know that. And what's the P2? Hey, look at here. We know the P2. And we can look up R. Hey, we could find V2. See it? Now, once you get V2, you can get the mass. The mass is going to be your volume divided by your little V2. What's the volume? 5 cubic feet. Hey, we can get the mass. You see it? Now, I'm going to write this for you. This is 15 psi. Need some room here. 15 psi times V2 equals R. Now, R is 5334 foot-pounds force per pound mass Rankine, and the Rankine is 740.3 Rankine. Now, here's your equation. See it? We can get V2. Yeah. And once we get V2, we can get the mass, because we know what the volume is. It's 5 cubic feet. Now I'm going to shut up again, and I'm going to let you. I mean, you can sit there and be bored and watch me do stuff, but you need to do that. Now, don't forget, you have to get these units to work right. If you forget something about the units, you're going to get the wrong answer. I won't tell you the dirty secret, but there is a dirty secret here that you've got to do something to get the units to work. All right, go for it. Find V2 for me. Here goes. Well, I did that, and I got V2. Did you get 18.28 cubic feet per pound mass? If you did, say, uh-huh.
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 There's one. Oh, there's another one. We did good. And now we can get the mass. The mass is going to be 5 cubic feet divided by that V2. Go for that. See what we get. I've got the mass. I think it's 0.2735 pound mass. So we have the mass. If you got that, say, uh-huh. Yeah, there's one.
Uh-huh.
There we go. Good going. Now, what else are we supposed to do? Let me read this again here. 7141A. Find the mass. Okay, we did that. And the entropy generation. Well, to do that, we're going to need the second law again. And I need some room here. I hate to sacrifice all this wonderful stuff. And we haven't even done our PV and TS diagrams. Dang. Well, maybe we can. We'll see what we can do. I just need some room here. Now let's do our second law to get that entropy generation. Now the way that's going to go is M2 U2, no, not U2, that's the first law, M2 S2, there you go, minus M1 S1. Well, it was empty. There is no M1. It's empty. So it's minus 0 equals the heat transfer term. It's adiabatic. Didn't they say adiabatic? Let me read this. 141E. Assume no heat transfer. We don't need to worry about the heat transfer. It's 0 plus the generated entropy plus the entropy coming in. That would be Mi little si minus the entropy going out. Well, there isn't any. There's no exit. All right, now let's see what we know. Do we know M2? Yeah, look at here. We got M2. Let me circle that. Now do we know S2? Well, here's what I'm going to do. Isn't Mi the same as M2? Here's what I'm going to do. Watch the algebra here. I'm going to say that generated entropy is equal to M2 little s2 minus little si. I did a little algebra there. Can you get there? See, the M2 and the Mi are the same, so you could put Mi in there. It's the same thing. They're the same. Whatever comes in is what you got left. And we know what it is. We solved it. We know that. But how are we going to do this? Well, we have an equation that goes like this. Now let's see what we know out of these terms. We could look up C sub P for air. I have no doubt that we could do that. Do we know T2? Well, yeah, we do, only that's in Fahrenheit. It's got to be in Rankine. Do we know TI? I think I lost it, but I think we can retrieve it. Do we know R? Yeah, we know R. Do we know P2? Yeah. Well, where'd it go? Oh, gee. We know what it is, but I think I erased it, dang it.
15.
Oh, yeah. Good thinking. Because when you open that valve and you leave it open, it just, hey, doesn't this term drop out? Isn't the P2 and the P1 the same? Right? I think so. Yeah. And the natural log of 1 is 0. This whole term drops out. Isn't that nice? And I know what this is. From memory, it is, I think it's 0.24. BTUs per pound, but we probably should look it up. But these have got to be in Rankine. Did I do that right?
That CP is, yeah, that's correct.
Now we just need the temperatures. The T1, we had it on the board, but let me just come up with close. It's 70 plus roughly it's 460. It's 459 something, but that's close enough. Basically, it's 530. And we're going to divide by the, no, that's the incoming. We'll divide by the 530. But the T2, that's the hot one. I believe that's a 740. That's a 740.3 Rankine. And the 530 is the incoming Rankine. And so we're going to get this here. But we won't be through yet because then you have to multiply by the mass. But we can get this much. Let's do that. Here goes. Oh, gee, we're running out of time. Take the natural log of that times 0.24. Okay, I got that. And now I'm going to multiply by M2. Where'd M2 go? There it is. 0.2735. And here's what I'm coming up with. The generated entropy in this problem is 0.0219 BTUs per Rankine. See, we got rid of the pound masses when we multiplied here. And the answer book says, the answer book says 0.022. In the back, does that show up? Not very good. The answer book says 0.022. So I think we did pretty good. Oh, but now wait a minute, we didn't get our PV and TS diagrams, dang. Oh, it's so sad. I have 60 seconds left though. I bet we could get the PV diagram. Hey, there's some room over here. It's air, so we don't do any vapor dome. We don't need no stinking vapor dome. So don't put it in. Let's put in that 70 Fahrenheit though. Yeah, there you go, 70 Fahrenheit. What is the final temperature? Oh, gee, it's 280.
280.
Yeah, that's 280.6. Gee, our time is up. It's so sad. What about the pressure? What did the pressure? Oh, it went way up, didn't it? It started off down here at 15 PSI, and then it went way up to what? I got lost. Anybody
I
remember?
thought the pressure couldn't go any higher than 15 psi.
Oh, good thinking. Good thinking. It did this. There's your 15 psi. There's your initial state. There's your final state. It stayed at 15 psi, but the temperature went way up. Oh, it's sad, but our time together has come to an end, and we're going to have to say goodbye. Parting is such sweet sorrow. Do you have any last things to say? Well, I hope you had as much fun as I did. Go ahead.
Yeah, just thank you. Thank you very much.
Oh, you are so very welcome. And I will see you Thursday at 11. How's that?
See you Thursday.
Okay, ta-ta, everybody. Bye-bye.
Bye. Have a good day, sir.
Bye-bye for now.